The sky above us is not a static painting, but a living, breathing arena of constant change. Astronomers are now forecasting a series of cosmic events that will unfold in our near future. A celestial timeline packed with both breathtaking beauty and profound danger. By the end of this journey, you will know the 25 specific cosmic predictions that could redefine our place in the universe. We will witness a star exploding into a temporary second moon and confront a solar storm capable of reshaping modern civilization. What single cosmic event are you most curious to see become a reality? Our sun is stirring from its slumber, and the consequences could soon be felt right here on Earth. The first major event on our cosmic timeline is the Great Solar Storm of 2025. This prediction stems from the sun's natural rhythm, an 11-year cycle where its magnetic field flips and its activity surges to a peak. We are currently climbing toward that solar maximum, a period of intense turmoil on the star we call home. During this peak, the sun can unleash titanic eruptions known as solar flares, sudden flashes of radiation that travel at the speed of light. Even more consequential are coronal mass ejections, or CMEs. These are billion-ton clouds of magnetized plasma hurled from the sun's outer atmosphere, and when one is aimed directly at us, it can trigger a planetary-scale emergency. The immediate effect could be one of breathtaking beauty. A truly powerful CME slamming into Earth's magnetic field would supercharge our atmosphere, creating auroras so brilliant they could be seen from cities like Rome and Tokyo. The night sky would dance with curtains of green, red, and purple, a celestial light show visible to billions, but this beauty comes with a devastating price. That same incoming storm carries a massive electrical charge. It would induce powerful currents in the ground itself, currents that would seek the path of least resistance, surging directly into our continental power grids. The result could be widespread, long-lasting blackouts, not for hours, but potentially for weeks or even months. Imagine a world without stable electricity, where communication networks fail, water treatment plants shut down, and refrigeration becomes a luxury. Our global fleet of satellites, the backbone of GPS and global communications, would be bombarded with radiation, potentially crippling thousands of them in a single event. This is not science fiction, it is a realistic risk based on our understanding of solar physics. The last storm of this magnitude, known as the Carrington event, occurred in 1859, long before our world became utterly dependent on electronics and power. The next one is not a matter of if, but when, and many scientists believe the when could be very soon. While our own sun poses a terrestrial threat, a different kind of stellar drama is unfolding 640 light-years away. The red supergiant star Betelgeuse, the fiery shoulder of the constellation Orion, is behaving strangely. This colossal star is a ticking time bomb, and astronomers are on high alert for the ultimate cosmic spectacle, a supernova. Betelgeuse has already dimmed and brightened in unprecedented ways, leading many to wonder if these are the final convulsions before its dramatic end. The signs they are watching for are specific and profound. A sudden, extreme dimming could signal that the star is collapsing inward, a necessary prelude to the explosion. Then, within a day, a flood of nearly invisible particles called neutrinos would silently pass through the Earth, detected by special observatories deep underground. This would be our first official warning that the star's core has imploded. Only hours later, the light would arrive. The explosion would not be a quick flash. It would be a new, permanent star in our sky, blazing with the intensity of a full moon. Imagine a brilliant, unwavering diamond visible even during the day, casting faint shadows at night for weeks or even months before slowly fading away. This would not just be a beautiful sight, it would be a scientific bonanza. For the first time in centuries, astronomers would have a front-row seat to the death of a massive star. They could study the formation of heavy elements like gold and uranium in real time, watch a neutron star or black hole being born, and gain unprecedented insight into the life cycles that govern the universe itself. This singular event would transform our understanding of cosmic evolution, all from the safe distance of a spectacular light in the heavens. That stellar explosion would be a distant wonder, but a much closer cosmic visitor is already on a precise trajectory toward our world. In April of 2029, the asteroid known as Apophis will make a close pass by Earth, sweeping nearer to our planet than the very satellites that broadcast our television signals. This is not a Hollywood disaster plot. It is a real-world astronomical event that you will be able to witness with your own eyes. Apophis is a formidable rock, measuring over 1,000 feet across. It will be hurtling past us at an astonishing speed of nearly 25,000 miles per hour. At its absolute closest approach, it will be a mere 20,000 miles above the Earth's surface, appearing as a fast-moving point of light streaking through the night sky. For a short time, it will outshine the stars in some of the most familiar constellations, a visible reminder of the dynamic solar system we inhabit. The crucial fact, however, is that Apophis will not strike us. Extensive tracking by astronomers using radar and optical telescopes has definitively ruled out any chance of an impact for at least the next century. This flyby is not a threat, but a generational opportunity. Scientists are preparing to turn every available instrument toward this visitor. They will study its composition, its rotation, and how its path is subtly altered by Earth's gravity, data that is vital for our long-term planetary defense. For the rest of us, it is a chance to simply look up and participate in a shared moment of cosmic awe, watching a mountain-sized relic from the dawn of the solar system make its graceful and harmless pass. While we can track asteroids with precision, the most breathtaking sights in the sky often arrive without warning. The fourth cosmic event is the inevitable appearance of the next great naked-eye comet, a brilliant and unpredictable wanderer that could light up our heavens at any moment. These icy travelers originate from the frozen depths of the solar system, in a distant cloud of debris far beyond Pluto. Most remain in that deep freeze, but occasionally, a gravitational nudge from a passing star sends one plummeting toward the inner solar system. As it approaches the Sun, the heat begins to vaporize its ancient ice, releasing dust and gas that form a vast, glowing cloud around the nucleus, called the coma. The solar wind and radiation pressure then push this material away, creating the comet's iconic tail, which can stretch for millions of miles, always pointing away from the Sun. A truly spectacular comet possesses two key features: a brilliant, star-like head, and a long, gracefully arching tail that dominates a portion of the night sky. Its appearance is not a brief flash, but a slow, majestic drift against the backdrop of stars, visible for weeks. The scientific value is immense, as each comet is a pristine sample of the solar system's original building blocks, a frozen time capsule holding clues to the origin of Earth's water, and perhaps even the organic ingredients for life. But beyond the science, a great comet is a profound cultural event. It is a shared celestial experience that transcends borders, reminding everyone who looks up that we are all passengers on the same planet, gazing out at the same magnificent and dynamic cosmos. The question is not if, but when the next one will arrive, turning its fleeting beauty into a global moment of collective wonder. Far beyond the sporadic flash of a supernova lies a cosmic event of almost unimaginable power. A nearby gamma-ray burst is one of the most cataclysmic phenomena in the entire universe, a tightly focused beam of pure energy that can, for a few fleeting seconds, outshine every star in a galaxy combined. While the chance of one occurring close enough to affect us is incredibly small, its inclusion on this list is a necessity, a reminder of the raw forces at play in the cosmos. These bursts are the death cries of the most massive stars or the final, violent embrace of colliding neutron stars. When a star many times heavier than our Sun exhausts its fuel, it can collapse not into a supernova, but into a hypernova, a far more energetic explosion that forges twin jets of gamma radiation firing from its poles like a cosmic blowtorch. Alternatively, when two ultra-dense neutron stars spiral into each other, their merger ripples spacetime and also launches these devastating beams into the void. If such a beam were pointed directly at Earth from a nearby galaxy, the consequences would be stark. The initial flash of gamma rays would be harmless to life on the surface, but it would violently rip through our upper atmosphere. It would smash into molecules of nitrogen and oxygen, breaking them apart and sparking a chain of chemical reactions. The result would be the creation of vast quantities of nitrogen oxides, compounds that act like a corrosive smog. This smog would begin to eat away at our planet's ozone layer, the essential shield that protects all life from the sun's harmful ultraviolet radiation. A sufficiently powerful and close burst could potentially strip away a significant portion of this protective layer over months or years, leading to a dramatic increase in UV exposure at the surface. The silver lining, and it is a crucial one, is that such an event in our galactic neighborhood is exceedingly rare. The universe is vast, and these deadly beams are narrow. The odds of one being aimed precisely at us from a dangerous proximity are astronomically low. Yet the mere existence of such power, a force capable of altering a planet's atmosphere across millions of light years, forces us to acknowledge the true scale of the universe's violence, a reminder that we orbit a quiet star in a sometimes quiet neighborhood, but the wider cosmos holds energies beyond our full comprehension. From the terrifying power of distant stellar explosions, we turn our gaze to a new machine of pure discovery, one designed not to witness destruction, but to find creation. The sixth event is the planned launch of the James Webb Space Telescope's successor, an observatory so advanced it will make our current view of the cosmos seem like a fleeting glimpse. While the James Webb Telescope revolutionized our understanding of the early universe, its successor is being designed with an even more profound goal: to directly seek out signs of life on worlds orbiting other stars. This new telescope will possess a mirror vastly larger than Webb's, granting it an incredible light-gathering power. It will see in wavelengths of light that are ideal for studying the atmospheres of distant exoplanets. Imagine pointing this incredible instrument at a small, rocky planet dozens of light-years away. It would not see a dot of light, but would instead capture the planet's atmospheric spectrum, a unique chemical fingerprint imprinted on the starlight filtering through its air. Scientists will scan that data for the telltale signs of biosignatures, combinations of gases that, on Earth, are produced by living organisms. The simultaneous presence of oxygen and methane, for instance, is a powerful indicator, as these gases rapidly destroy each other unless they are constantly replenished by life. This telescope could analyze hundreds of such worlds, moving from simply finding planets in the habitable zone to determining which ones are actually inhabited. It will also peer back to the very first billion years after the Big Bang, witnessing the birth of the very first stars and galaxies in unprecedented detail, seeing them not as faint smudges but as resolved structures. This is more than just a new tool. It is a philosophical leap, a machine built to answer the ancient question of whether we are alone in the universe, transforming one of humanity's greatest mysteries into a problem of data analysis. The legacy of the James Webb Telescope is the discovery of a universe brimming with potential, and its successor will be the instrument that tells us if that potential has been realized elsewhere. The search for life on distant worlds is a quest of pure observation, but humanity is preparing to take a far more active role in its cosmic future. The seventh great event is the first crewed mission to Mars, a venture that will mark our official transition from a single planet species to an interplanetary one. Multiple space agencies and private companies are now converging on a timeline with ambitious targets set for the 2030s. The journey itself is a monumental undertaking. A one-way trip to the Red Planet will take roughly 6 to 9 months, depending on the ever-changing alignment of our two worlds. During that long transit, the crew will be utterly isolated, confined within a small spacecraft as they traverse the deep, radiation-filled void between planets. They will have to live with recycled air and water, maintain their own physical and mental health in microgravity, and operate with a communication delay of up to 20 minutes each way, making real-time conversations with mission control impossible. Upon arrival, the challenges only intensify. The first human explorers will likely not land on the surface immediately. Instead, they may first enter orbit, perhaps docking with a pre-positioned habitat module that will serve as their initial base camp. Their primary goals will be foundational, testing systems for long-term survival, conducting preliminary surface surveys from orbit, and proving that humans can live and work in the Martian environment for extended periods. The ultimate objective of these initial missions is to establish a permanent, sustainable presence. This means learning to live off the land, extracting water from subsurface ice deposits, and using the Martian soil and atmosphere to create oxygen for breathing and fuel for the return journey. Every step will be a historic first, from the first human footprint in the rust-colored dust to the first structure built by human hands on another world. This is more than just an engineering challenge, it is the next great chapter in the human story. It represents a collective step outward, a declaration that our future is not tied to one world, but stretches toward the horizon of countless others. Our ambition to become an interplanetary species hinges on finding the fundamental ingredient for life, and we may not need to travel to another star to find it. The eighth cosmic event is the hunt for liquid water on Jupiter's moon Europa, a world that looks more like a cracked marble than a barren rock. Beneath its icy crust, scientists are almost certain a global ocean exists, containing more than twice the liquid water of all Earth's oceans combined. This makes Europa one of the most promising places in our entire solar system to search for life beyond Earth. The key to unlocking this mystery is the Europa Clipper mission, scheduled to launch in the coming years. This spacecraft will not land on the surface. Instead, it will perform a series of daring close flybys, sweeping over the moon's fractured terrain to map its hidden ocean and study the composition of its ice shell. Its sophisticated suite of instruments is designed to act like a remote laboratory. Cameras will capture the surface in stunning detail, looking for fresh cracks and chaotic terrain that hint at geologic activity below. An ice-penetrating radar will peer directly through the frozen crust, measuring its thickness and searching for pockets of slushy water closer to the surface. The most exciting possibility, however, involves plumes. There is strong evidence that Europa, much like Saturn's moon Enceladus, occasionally erupts, sending gigantic geysers of water vapor and ice particles shooting out into space from its hidden ocean. If the Clipper flies through one of these plumes, its mass spectrometers will have a direct sample of the ocean's chemistry. They will analyze the material, searching for complex organic molecules, the carbon-based building blocks essential for life as we know it. Finding evidence of a liquid water ocean is one thing, but discovering the chemical ingredients for biology within it would be a paradigm-shifting event. It would tell us that the recipe for life is not unique to Earth, and that the universe might be teeming with habitable environments right in our own cosmic backyard. This mission is not just about confirming an ocean, it is about taking the first real step toward answering whether we are alone. The oceans of Europa represent a profound mystery, but our next great leap requires a foothold much closer to home. Orbiting the Moon, a new outpost is slowly taking shape, a project known as the Lunar Gateway. This is not merely another space station, it is a deep spaceport designed to be humanity's first permanent presence beyond Earth's immediate grasp. The Gateway will serve as a command module, a science lab, and a safe house for astronauts preparing to descend to the lunar surface. Unlike the International Space Station, which circles Earth, this new station will travel in a unique, highly elliptical orbit around the Moon, offering access to almost the entire lunar surface. Its core purpose is to enable a sustainable return to the Moon. Imagine crews launching from Earth to rendezvous with this orbital waypoint. They would then transfer into a dedicated lunar lander, descending to the South Pole to explore, before returning to the gateway to refuel and resupply for their next sortie. This modular approach, much like establishing a base camp on a mountain before attempting the summit, makes complex lunar operations far more efficient. This is an immense international endeavor, bringing together the space agencies of the United States, Europe, Japan, Canada, and the United Arab Emirates. Each partner is contributing a critical piece, from habitation modules and robotic arms to advanced power and propulsion systems. But the Gateway's vision extends far beyond the Moon. Every system on board, from life support that recycles air and water for months on end to the protocols for managing long-duration missions far from Earth, is a direct test for the technologies we will need to send humans to Mars. It is a proving ground in the harsh environment of cislunar space, where we will learn to live and work productively while isolated from our home planet. The completion of the Lunar Gateway is the foundational step, the construction of the dock from which the ships to other worlds will one day depart. While the Lunar Gateway serves as our orbital foothold, a world of pure geological chaos orbits just beyond it. Jupiter's moon Io is a vision of hellish beauty, its surface a constantly changing canvas of fiery eruptions and flowing lava. As the most volcanically active body in the entire solar system, its next major outburst is not a matter of speculation, but an event we can actively predict. Astronomers are now using decades of data to forecast the next great volcanic event on this strange moon. By analyzing the patterns of past eruptions, they can identify which of Io's hundreds of active volcanoes is most likely to blow next. These are not small events. A major eruption on Io can spew fountains of lava dozens of miles high, creating vast new lakes of molten rock that visibly reshape the Moon's orange and yellow landscape in a matter of weeks. The driving force behind this incredible activity is not internal radioactivity, as on Earth, but the relentless gravitational tug of war between Jupiter and its other large moons. This process, known as tidal heating, constantly squeezes and stretches Io's interior, generating immense friction that keeps its rocky mantle in a semi-molten state. Predicting the next big eruption gives scientists a rare opportunity. It allows them to point the world's most powerful telescopes at a specific location in advance, capturing the entire life cycle of a volcanic event from its sudden onset to its slow decline. Watching how these lava flows cool and what gases are released provides a living laboratory for understanding the most extreme forms of planetary geology. It is a stark reminder that worlds are not static, and that the same forces that gently lift our ocean tides can, under the right conditions, turn an entire moon into a cosmic pressure cooker, forever remaking itself before our eyes. The dream of finding another Earth is on the verge of becoming a statistical certainty. Within the next few years, powerful new telescopes will almost certainly identify the first truly Earth-sized planet, orbiting comfortably within the habitable zone of a sun-like star. This discovery will hinge on two primary methods of detection. The first is the transit method, where a telescope stares at a star, waiting for the telltale, periodic dimming that occurs when a planet crosses directly in front of it. The depth of that dimming reveals the planet's size, allowing us to distinguish a gas giant from a small, rocky world like our own. The second method measures the stellar wobble. A planet's gravity doesn't just make its star the center of the system. The two bodies actually orbit a common center of mass. This causes the star to wobble back and forth ever so slightly, a motion that can be detected by the subtle shifts in the color of its light. By combining the transit data, which gives us the planet's size, with the wobble data, which gives us its mass, we can calculate its density. And a world with a density similar to Earth's is almost certainly a rocky planet, the first prerequisite for being Earth-like. But finding a rocky world in the habitable zone is only the beginning. The true revolution comes with the next step, atmospheric spectroscopy. When the planet transits its star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to our telescopes. That atmosphere imprints a unique chemical fingerprint on the light. By splitting that light into a rainbow of colors, a spectrum, scientists can read that fingerprint. They will search for the biosignatures we associate with a living world. The simultaneous presence of oxygen and methane would be a powerful clue, as these gases quickly react and destroy each other unless they are constantly replenished, likely by biological processes. Finding water vapor would be another critical piece of evidence. This is not about seeing alien cities or receiving radio signals. It is about analyzing the very air of another world from dozens of light years away and concluding that the chemistry is so strange, so out of equilibrium, that it can only be explained by the presence of life. The discovery of such a world would transform our place in the cosmos, changing the question from whether life exists elsewhere to how common it truly is. This rare celestial gathering will offer an unprecedented opportunity for direct comparison. Through a telescope, the differences between these giants will be starkly visible. Jupiter will appear as a brilliant, banded disk, its great red spot a persistent storm larger than our entire planet, flanked by its 4 largest moons dancing in a line. Just beside it, Saturn will showcase its breathtaking ring system, a delicate, icy structure tilted at a precise angle, making it look like a jewel suspended in the void. Further out, the ice giants Uranus and Neptune will reveal themselves as smaller, perfect aquamarine marbles, their deep blue hues a result of methane in their atmospheres absorbing red light. Seeing them together in one field of view transforms them from abstract points of light into a family of worlds, each with its own unique personality and mysteries. The scientific value of such an alignment is immense. It allows astronomers to study the atmospheres of all 4 planets in rapid succession under similar observing conditions, providing a snapshot of weather patterns across the outer solar system. We could monitor the raging storms on Jupiter, the hexagonal jet stream at Saturn's North Pole, and the supersonic winds of Neptune all within a single night. This side-by-side comparison helps us understand the fundamental principles of planetary formation and evolution, revealing why these worlds, born from the same primordial cloud of gas and dust, grew to be so different. This grand alignment is more than a pretty picture. It is a cosmic classroom, a chance to read the history of our solar system written in the light of these distant, wandering giants. The first historic image of a black hole was not an ending, but a beginning. Now, the next great leap is to turn that single, blurry portrait of M87's core into a full-motion picture of our own galactic center, Sagittarius A star. The Event Horizon Telescope collaboration is pushing its global network of observatories to a new frontier, aiming to capture not just a snapshot, but a video of superheated gas as it whips around the event horizon at nearly the speed of light. This is an immense technical challenge. Creating that first image required combining data from telescopes across the planet, a process likened to reading the date on a coin in New York from a sidewalk in Los Angeles. To make a movie, they need to capture multiple such images in rapid succession, essentially requiring a telescope with a shutter speed fast enough to freeze the motion of the most chaotic environment in the galaxy. The gas and dust orbiting SGR A star complete a full circle in just 30 to 40 minutes, meaning its appearance changes on a timescale of mere seconds. To see this dance, astronomers are adding new telescopes to the array, and developing sophisticated algorithms to fill in the gaps between the fleeting moments of observation. What will this movie reveal? We will witness the dynamic flow of the accretion disk itself, watching as magnetic fields twist and snap, launching jets of material into the void. We could see bright knots of plasma, glowing as they are stretched by unimaginable tidal forces, their light warping and lensing around the central darkness in real time. This is not just about seeing a black hole spin. It is about watching Einstein's theory of general relativity play out in a violent, real-world laboratory. It will show us how these cosmic engines consume matter and energy, transforming our understanding of spacetime itself from a theoretical concept into a visible, dynamic force. The first frame of that movie will be one of the most profound scientific achievements of our time, a window into the heart of darkness that powers our entire galaxy. Deep within the cosmic noise, a sudden and brilliant flash of radio energy can outshine an entire galaxy for a few fleeting milliseconds. These are fast radio bursts, and their brief, unpredictable nature has made them one of astronomy's most stubborn puzzles. But a key piece of this mystery is about to be unlocked. As new observatories are poised to decode the signals from bursts that do something extraordinary, they repeat. Unlike a single, catastrophic event, repeating FRBs offer a second chance, an opportunity to point the world's most powerful radio dishes back at the same patch of sky and listen again. The leading suspect for at least some of these repeating enigmas is a magnetar, a type of neutron star with a magnetic field so intensely powerful it could strip the data from every credit card on Earth from half the distance to the Moon. The theory suggests that starquakes on the surface of a magnetar, or sudden rearrangements of its monstrous magnetic field, could crackle with these powerful radio flashes. Another possibility involves a highly magnetized neutron star in a tight orbit with a companion, where interactions between the two bodies periodically trigger immense releases of energy. As these repeating signals are captured again and again by new telescopes like the Canadian CHIME and the upcoming Deep Synoptic Array, scientists will amass a vast library of their unique fingerprints. They will analyze the precise structure of each pulse, how the radio waves are twisted by magnetic fields, and how the bursts evolve over time. This wealth of data will allow them to distinguish between the proposed sources, much like a detective comparing bullet casings from a series of crimes. If the data points conclusively to magnetars, it confirms these exotic stellar corpses as engines of one of the universe's most energetic phenomena. But if the evidence doesn't fit, it forces us to consider even more exotic origins, perhaps involving cosmic strings or other theoretical objects predicted by physics but never before seen. Solving the mystery of repeating fast radio bursts is more than just identifying a source. It is about opening a new window onto the most extreme and dynamic environments in the cosmos, revealing processes of energy release we are only beginning to comprehend. A shattered comet is now scattering its remains along Earth's orbital highway, and we are scheduled for a direct encounter. This is the potential birth of a brand new meteor shower, an event born from celestial destruction. When a comet fractures, it doesn't just vanish. It leaves behind a vast and diffuse river of dust, ice, and rock, a debris stream that continues to orbit the Sun. Astronomers are now becoming adept at mapping these cosmic minefields. By calculating the precise orbits of both Earth and these dispersed particles, they can predict when our planet will plow directly through the densest part of the cloud. The result would be a sudden, spectacular display of shooting stars, all appearing to radiate from a single point in the sky. But there is a chance for something even more extraordinary, a meteor storm. This is not just a gentle shower. In a true storm, the sky could ignite with thousands of meteors every hour, a silent, breathtaking fireworks display of nature's own making. Each streak of light would be a piece of that shattered comet, some no larger than a grain of sand, vaporizing in a final, brilliant flash as it hits our atmosphere at tens of thousands of miles per hour. Unlike annual showers that can be reliable but often modest, a new shower born from a recent breakup holds the potential for a genuine surprise, a deluge of cosmic gravel that has never been seen by human eyes before. It is a reminder that the solar system is a dynamic and sometimes violent place, where the death of one celestial object can gift the sky above us with a fleeting, beautiful rebirth. The silent void above our planet is no longer so empty. It is now a bustling orbital highway, but one increasingly littered with the ghosts of our own ambition. This leads us to the 16th cosmic event, a sobering prediction not of natural phenomena, but of a man-made crisis, the potential trigger of Kessler syndrome. The concept is as simple as it is terrifying, a cascade of collisions in low Earth orbit. Imagine a single piece of debris, perhaps a stray bolt from an old rocket or a fragment from a satellite that exploded, colliding with a functioning satellite. That impact doesn't just disable the satellite, it shatters both objects into thousands of new, smaller pieces of shrapnel. Each of those new fragments now becomes a high-speed projectile, capable of destroying another satellite and creating even more debris. This can initiate a chain reaction, a domino effect of destruction where each collision fuels the next, creating an ever-expanding cloud of deadly orbital shrapnel. The risk is not just to future missions, but to everything we already have up there. The International Space Station, a symbol of global cooperation, must regularly perform maneuvers to dodge known pieces of this junk. Our vital infrastructure, the satellites that provide GPS, weather forecasting, and global communications, would be living in a shooting gallery. A full-blown Kessler cascade could render entire orbital altitudes unusable for generations, trapping us on our planet behind a barrier of our own making. The urgency of this prediction has sparked a new frontier in space technology: active debris removal. Companies and agencies are now testing concepts like robotic arms, nets, and harpoons designed to literally capture and deorbit defunct satellites. Others are developing spacecraft that use magnetic tethers or powerful lasers to nudge debris downward, where it will safely burn up in the atmosphere. This is coupled with a push for sustainable space practices, demanding that new satellites have built-in systems to propel themselves into a disposal orbit at the end of their lives. This event is a stark reminder that our future in the cosmos depends not just on reaching outward, but also on cleaning up after ourselves, ensuring the pathways to the stars remain open for those who follow. Our orbital environment is about to transform from a realm of government outposts into a marketplace of private enterprise. The 17th cosmic event is the launch of the first fully operational private space station, a development that will fundamentally change our relationship with the space above us. Companies like Axiom Space and others are leading this charge, constructing modular habitats designed to dock with the International Space Station before eventually flying free as their own independent destinations. These stations are not conceived as purely scientific outposts, but as versatile commercial hubs. Their business model relies on multiple revenue streams, opening the cosmos to a new class of customers. Space tourism will be a primary focus, offering paying clients the chance to experience microgravity and the breathtaking view of Earth from orbit for days at a time, not just minutes. But the vision extends far beyond luxury getaways. The unique environment of space offers unparalleled advantages for manufacturing. In the persistent microgravity, materials can be combined in ways impossible on Earth, leading to the creation of flawless fiber optic cables, perfect pharmaceutical crystals, and revolutionary new alloys. Research and development will also be a major tenet, with corporations leasing lab space to conduct experiments in biology, fluid physics, and medicine, all benefiting from the absence of gravity's distorting effects. This shift from government-led programs to commercial infrastructure is monumental. It mirrors the early days of aviation, when mail routes flown by government pilots eventually gave way to a global, private airline industry. These private stations represent the first true real estate in orbit, the foundational pieces of a space-based economy where services are bought and sold. They signal that humanity's future in space will not be solely driven by national flags, but by innovation, commerce, and the dream of making life in space an ordinary, accessible reality. Beyond the familiar planets, our solar system is enveloped by a vast, spherical shell of frozen relics. This is our own Oort cloud, a predicted but unseen frontier where trillions of icy bodies drift in the deep freeze. Now, for the first time, astronomers are on the verge of spotting a similar structure around another star. The discovery of an exo-Oort cloud will require the most sensitive telescopes ever built, instruments capable of detecting not the individual objects, which are far too small and dim, but their collective faint glow. This would appear as a persistent, ethereal halo of infrared light surrounding the star, the accumulated warmth from countless frozen worlds. Finding such a structure would be a monumental leap in our understanding. It would tell us that the architecture of our own solar system is not unique. The process that scattered icy bodies to the outermost reaches during our system's violent youth appears to be a universal rule, a standard part of planetary formation. This has a profound implication for interstellar travel. If most stars are surrounded by their own swarms of cometary material, then any future spacecraft venturing between stars would have to navigate a minefield of unseen, frozen objects. But the most thrilling consequence involves the visitors to our own system. We have already witnessed two interstellar objects, Oumuamua and Borisov, pass through our neighborhood. The discovery of exo-Oort clouds would provide the source for these wanderers. It suggests that gravitational nudges from passing stars can eject trillions of comets from their own cloud, sending them on journeys between the stars. Some of these castaways inevitably find their way into our own cosmic backyard, making every comet we see not just a messenger from our past, but a potential tourist from a star system we have yet to map. The rocks of Mars are about to tell their story. The 19th cosmic event is the culmination of decades of exploration, a multi-stage technological ballet designed to bring pieces of another world back to our own. This is the Mars Sample Return Mission, an interplanetary relay race involving rovers, rockets, and an orbital rendezvous. The first leg is already complete. The Perseverance rover is currently traversing Jezero Crater, a site chosen because it once held a vast lake. Its mechanical arm is carefully selecting and sealing pristine samples of Martian soil and rock into ultra-clean tubes, caching them on the surface for a future runner to collect. The next phase is even more audacious. A separate mission will launch from Earth, sending a lander to touch down near that cache. This lander will carry a small fetch rover, designed to swiftly retrieve the sample tubes and bring them back to the lander. Then, the most critical step begins. The samples will be loaded into a small, sturdy container about the size of a basketball, which will then be placed into a Mars ascent vehicle. This will be the first rocket ever launched from the surface of another planet, a fiery leap into the Martian sky to place the precious cargo into orbit. But the journey is only half over. Waiting in that orbit will be a European-built spacecraft, the Earth Return Orbiter. It must locate the sample container, capture it, and then seal it within a robust biocontainment system for the long cruise back to Earth. The final act will see this return capsule streak through our atmosphere and parachute down to a precise landing in a desert recovery zone. Once safely in a maximum security laboratory, scientists will finally open these time capsules. They will search for biosignatures, microscopic textures, or chemical patterns that could only have been formed by ancient Martian life. They will analyze the rocks to read the full climatic history of Mars, understanding exactly how and when a wet, potentially habitable world transformed into the dry desert we see today. This is not just about finding life. It is about understanding the very nature of planetary evolution, a story written in stone, soon to be delivered to our door. A silent, invisible wanderer could be drifting through the outer reaches of our solar system at this very moment. This is the prediction of a rogue stellar mass black hole, a ghost from a dead star, passing through our cosmic neighborhood. We would not see it with any telescope, for it emits no light. Its presence would be revealed only by the subtle, yet undeniable, tug of its gravity. Astronomers would detect its passage by watching the distant, frozen worlds of the Kuiper Belt and the Oort cloud. They would notice a strange perturbation, a distinct wobble or an unexpected shift in the orbits of these far-flung objects, as if an unseen hand were gently stirring the outer solar system. The path of long-period comets might be altered, their trajectories bent by a massive, invisible point. This is how we would map the shadow, by reading the ripples it leaves in the cosmic pond. The direct risk to Earth is almost non-existent, a statistical improbability given the vast emptiness of space. Yet the gravitational influence of such an object, even at a great distance, is profound. Its pull could potentially destabilize the delicate balance of our system, nudging asteroids from the main belt onto new and unpredictable paths. The greater fascination lies in the opportunity. A nearby stellar mass black hole would offer a pristine laboratory, a chance to study these enigmatic objects without the blinding glare of an accretion disk or the crowded heart of a galaxy. We could test the limits of general relativity with unparalleled precision, measure its mass through its gravitational lensing effect on background stars, and perhaps even detect the faint Hawking radiation theorized to emanate from its event horizon. This cosmic visitor would be a reminder that the universe is not only full of light, but also of dark, massive ghosts, and that sometimes, the most powerful forces are the ones we can never see. Deep beneath the Earth's surface, shielded from cosmic interference, a quiet revolution is underway. Scientists are hunting for the universe's most elusive substance, dark matter, and the next great breakthrough could come from a lab buried in a mine or an instrument floating in space. These experiments are designed to catch the uncatchable, to feel the faintest whisper of a particle that makes up over 80% of the universe's matter, yet has never been directly seen. The leading suspects have names that sound like science fiction, but they are grounded in serious physics. One candidate is the WIMP, or weakly interacting massive particle. These are theorized to be heavy, sluggish particles that rarely bump into ordinary matter, which is why trillions of them might be streaming through your body every second without you ever noticing. To find them, detectors use vats of ultra-pure liquid xenon, cooled to extreme temperatures deep underground. The hope is that on a very rare occasion, a passing WIMP will nudge the nucleus of a xenon atom, creating a tiny flash of light and a puff of electric charge that sensitive instruments can record. The other prime suspect is the action, a ghostly, lightweight particle that behaves less like a bullet and more like a wave. In powerful magnetic fields, an action might spontaneously convert into a faint microwave photon, a conversion that specialized dishes in space and on the ground are now listening for. Successfully identifying either one would be more than just a new discovery. It would be a complete rewriting of the rules. It would finally reveal the invisible scaffolding that holds galaxies together, preventing them from flying apart as they spin. We would understand the true composition of the cosmos for the first time, unlocking secrets about the universe's birth and its ultimate fate. This is the search for the universe's missing skeleton, a hunt for the ghost that gives the cosmos its shape. The silent darkness of the night sky, a canvas for human wonder for millennia, is now being silently rewritten. We are witnessing the rapid deployment of vast satellite constellations, networks of thousands of individual satellites working in concert to provide global internet coverage. These mega-constellations are designed to fly in low Earth orbit, and that proximity is what makes them so visually intrusive. Unlike the distant, fixed stars, These new artificial stars are in constant motion, crawling across the heavens in long, silent trains. For professional astronomers, this presents a crisis. The sensitive instruments of giant ground-based telescopes, which capture light that has traveled across the universe for billions of years, now have their observations scarred by the bright, streaking trails of these satellites. A single long exposure image of a distant galaxy can be rendered useless by multiple bright lines cutting across the frame, erasing priceless data. For the casual stargazer, the impact is more subtle but equally profound. The slow, majestic drift of a satellite across a starry field was once a rare novelty. Soon, it may become a constant presence, with dozens of these points of light visible at any given moment after sunset and before sunrise. The pristine view of the Milky Way, already a rarity for those living near cities, could be further compromised by a grid of moving dots, a permanent technological veil over the natural cosmos. This has sparked a fierce debate, a conflict between two powerful visions of the future. On one side is the promise of global connectivity, of bringing high-speed internet to every corner of the planet, enabling education, commerce, and communication for underserved populations. On the other side is the preservation of the night sky itself, a shared human heritage that has inspired art, science, and philosophy since the dawn of consciousness. Is the sacrifice of our universal view a necessary price for global progress? The conversation is pushing companies to find solutions, testing darker coatings and new orbital designs to reduce the reflectivity of their satellites. But as thousands more are launched, the fundamental question remains: are we creating a world where everyone is connected online, but no one can look up and see the universe that connects us all? This is not a distant prediction, but a transformation happening overhead right now, challenging us to decide what kind of sky we want to leave for the generations to come. That single discovery would shatter our cosmic solitude forever. The 23rd event is the one that has haunted human imagination for centuries, the first definitive discovery of extraterrestrial life. This monumental announcement will not arrive as a dramatic signal from an alien civilization, but more likely as a quiet, painstakingly verified data point. Scientists will find their evidence in one of two places: the ancient rocks of Mars or the distant air of another world. On Mars, the discovery could come from a returned sample, where researchers using powerful microscopes identify the microscopic fossils of long-dead Martian microbes. These would not be little green men, but subtle textures and chemical patterns etched into stone, shapes and structures that could not have been formed by geology alone. The alternative, and perhaps more probable, scenario unfolds light years away. A next-generation space telescope will analyze the atmosphere of an Earth-like exoplanet and detect a biosignature, a chemical imbalance that shouts the presence of biology. The most compelling would be the simultaneous detection of oxygen and methane. In a planet's atmosphere, these two gases are like fire and water. They rapidly destroy each other. To find them together in significant quantities means something on that world must be constantly replenishing them. And on our planet, that something is life. But scientists will not rush to the microphones after a single reading. The verification process will be exhaustive and deliberate. They must first rule out every possible non-biological source. Could geological processes or photochemical reactions mimic the signature? Could the reading be an artifact of the telescope itself? Multiple observatories will be tasked with observing the same planet, independently confirming the result. The data will be scrutinized, challenged, and peer-reviewed by teams across the globe. Only when every other explanation has been eliminated will the world hear the news. And when it does, the consequences will be as profound as any in human history. It will answer one of our oldest questions, confirming that life is not a singular accident on Earth, but a natural and perhaps common feature of the cosmos. Our perspective on our own planet will shift. transforming Earth from a unique sanctuary into a single specimen in a vast galactic garden. Philosophy, religion, and science will be forever altered, forced to accommodate a reality where we are no longer alone. This discovery would mark the end of humanity's childhood and the beginning of our true maturity as a species aware of its place in a living universe. The fabric of spacetime is not a silent stage, but a dynamic ocean of invisible waves. We now stand at the precipice of detecting the deepest, most resonant notes in this cosmic symphony, the low-frequency hum of supermassive black holes merging at the hearts of distant galaxies. This is the next frontier in gravitational wave astronomy, a hunt not for fleeting chirps, but for a persistent background rumble that has been building for billions of years. To hear this sound, scientists are using the universe's most precise natural clocks, pulsars. These are the rapidly spinning corpses of dead stars, beaming out radio waves with the metronomic regularity of an atomic clock. Astronomers are monitoring networks of these pulsing stars across our galaxy, creating a galaxy-spanning detector known as a pulsar timing array. They are listening for the most subtle of timing delays, a stagger in the perfect rhythm of these pulsars. The cause of this stagger would be a gravitational wave, a ripple in spacetime itself, gently stretching and compressing the vast distances between the pulsars and our telescopes as it passes through the galaxy. The source of these waves is not the collision of stellar mass black holes, but something far more colossal, the slow, inevitable dance of supermassive black holes, each weighing billions of times our Sun. When two galaxies merge, their central black holes eventually sink to the new core, locked in a gravitational embrace. They spiral inward over eons, and their final merger unleashes a titanic burst of gravitational waves that propagates across the entire universe. Detecting this background hum is like listening to the echo of every major galaxy collision in cosmic history. It would reveal the population of these binary behemoths and show us how the largest structures in the universe grew through a long and violent process of cannibalism. This is not just about confirming a theory. It is about opening our ears to the fundamental frequency of the cosmos, the base note underlying all of creation, a direct signal from the most powerful engines of gravity in existence. This final cosmic prediction brings our journey full circle, returning to the star that gives us life, but with a stark warning about its dormant power. We conclude with the event known as the Big One, a solar superstorm on the scale of the 1859 Carrington event. While our first event explored the solar maximum, this is the ultimate expression of that cycle's fury, a direct hit from a coronal mass ejection of historic proportions. In our modern, hyper-connected world, the consequences would be fundamentally different and far more severe than anything experienced in the 19th century. The initial impact would trigger a massive geomagnetic storm, inducing colossal electrical currents in the ground beneath our feet. These currents would seek out the most efficient pathways, which are the continents spanning high-voltage power lines and transformers that form the backbone of our electrical grid. These transformers are not built to handle such a massive, direct current surge. They would overheat, and many would fail catastrophically. Unlike a local blackout from a downed tree, these transformers are not items you can replace from a warehouse shelf. They are custom-built, multi-ton giants, manufactured overseas with lead times that can stretch to a year or more. The loss of hundreds of these critical nodes could plunge entire nations into darkness, not for days but for months. Imagine the cascading failure. Without stable power, water treatment plants cease to function. Fuel pumps at gas stations go silent. Refrigeration for food and medicine stops. Digital payment systems and ATM networks collapse, reverting society to a cash-based economy where physical currency rapidly vanishes. Our global communication network would be severed. Satellites in orbit, from GPS to telecommunications, would be fried by the intense radiation, their delicate electronics overwhelmed. Ground-based internet infrastructure, dependent on consistent power, would go offline. The world would be thrown into an information dark age, with radio silence between continents. The true vulnerability lies in the just-in-time delivery system that stocks our grocery stores and pharmacies. Without the constant flow of trucks, which rely on GPS and diesel fuel that requires electricity to pump, urban centers would face critical shortages within a matter of days. This is not a fictional doomsday scenario. It is a sober assessment of our deep technological dependency. The critical difference between 1859 and today is not the sun's violence, but our profound fragility. This prediction underscores the urgent, non-negotiable need for two things: advanced space weather forecasting and global infrastructure hardening. We must develop early warning systems that give power grid operators precious minutes to safely shut down systems before the storm wave hits. We must invest in protective devices that can block these geomagnetically induced currents and stockpile critical replacement transformers. The big one is a matter of when, not if. Its arrival will test the resilience of our civilization, forcing us to confront the delicate balance between our technological marvels and the raw, untamed power of our star. From breathtaking stellar explosions to the silent drift of interstellar comets, our journey reveals a future rich with both wonder and warning. We have charted a course from solar storms that could darken our cities to the discovery of life on a distant world, from the first human footprint on Mars to the ghostly passage of a rogue black hole. This cosmic timeline is not a distant fantasy, but a living forecast, a tapestry woven from the threads of celestial mechanics, human ingenuity, and profound mystery. Some of these events promise pure spectacle, a chance to simply look up and feel awe. Others challenge our very place in the cosmos, answering ancient questions while posing new ones. And a few serve as critical reminders of our fragility in a vast and sometimes violent universe. Each prediction is an invitation to participate in the greatest story ever told, the ongoing exploration of our home in the stars. The sky above is a dynamic stage, and the next act is about to begin. Your role is to stay curious, to follow the news as these cosmic predictions unfold, and to never forget the power of looking up. The greatest discoveries are still to come, and they are waiting for you just beyond the horizon.